Our webinar topic is Mind Meets Machine, the Evolution of Brain-Computer Interfaces. अब हम आगे स्लाइड्स में देखते हैं कि कैसे BCI evolve हुआ है.
It's kind of warm there now, I gather.
Yeah.
Yeah, our weather has just gotten nice. The winter's over.
Yeah, it's quite hot in here. Today, I think the maximum temperature was around 43 degrees in Islamabad.
Wow.
Also, I just
It's
came back from a
46 in
walk.
Multan.
Oh, 46. 46 in Multan. Wow.
So I'm glad you're working on FNIRS-based BCIs. That has gotten not as much attention as it probably deserves. No.
True.
So,
Yeah. Yeah. And in fact, recently we have started working on hybrid modalities BCI. So we're trying to
Right.
combine EEG and FNIRS now.
Yes.
Because FNIRS alone, you know, we were kind of stuck with the inherent delay of FNIRS. So I think it's important to use EEG along with FNIRS and make use of both these modalities.
No, that's yeah, okay. Have you published on that at all yet?
Yes, we have published. We have published on hybrid as well.
Okay. Well, we have to start. I have to start getting the background we'll need for the second edition of the book. We're just putting that together. So I'm doing it with Dean Krasinski.
Okay.
So that'll be important. I have to catch up on a lot of things that have happened. So have you been to the BCI meeting?
Yeah, I've been there a long time ago, but not recently.
Okay. Yeah, the society has their general meeting today, this afternoon. So.
Oh, I see.
If you haven't joined, you should join. It's becoming quite active.
Oh, okay, okay. I think I'll join it then.
Okay.
So, Saim, shall we start? Saim, are you here?
Sure, sir. We will start now.
Okay, okay.
Assalamu alaikum to the esteemed participants and respected guests, and welcome to this webinar of Bazm-e-BME. My name is 𝐌𝐢𝐧𝐝 and I am a third-year student in biomedical engineering from High-Tech University and a representative of Bazm-e-BME, and I will be your host for this webinar. The title of this webinar is Mind Meets Machine, the Evolution of Brain-Computer Interfaces. We are joined by Mr. Saim Gardezi, the founder of Bazm-e-BME. We are also joined by our esteemed guests who would share their thoughts and enlighten us regarding the topic. But first, I would like to give you all a brief introduction about Bazm-e-BME. Biomedical engineering is our beloved field, and for the promotion of this field in Pakistan, the Bazm-e-BME Society was established in August 2022. Bazm is an Urdu word having the meaning a pleasant gathering. Bazm-e-BME is a society that is trying to create a connection between all the students and professionals of biomedical engineering in Pakistan and is providing necessary guidance and support accordingly. The main motive of this society is to do positive and valuable efforts for sharing the knowledge of biomedical engineering in Pakistan. Now, Bazm-e-BME has more than 960 industrious and enthusiastic members from almost all the major universities of Pakistan. Bazm-e-BME is a guiding light for the future of biomedical engineering in Pakistan, with its goal to share the importance of biomedical engineering across the country and its top-level research and development work. Bazm-e-BME is set to make a big impact on the lives of Pakistanis. It aims to train a new generation of biomedical engineers who will lead the way in solving Pakistan's healthcare problems. Before going further, I would like to invite Mr. Sufyan Shah to recite a few verses from the Holy Quran.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم قل هو الله أحد الله الصمد لم يلد ولم يولد ولم يكن له كفوا أحد. Translation. Say, He is Allah, the only one. Allah, the one taking care of everything. He did not give birth, and he was not born, and he never had any equal at all. صدق الله العلي العظيم. Jazakallah.
Jazakallah, Mr. Sufyan, for reciting the holy verses in your soulful voice. Now, I would like to introduce you to our first guest, Dr. Numan Nasir. Dr. Numan adds a new dimension of excellence and expertise to our community. He has remarkable accomplishments and contributions to the field of mechatronics and biomedical engineering. He is among the top 2% scientists of the world for consecutive 2 years. He is also senior member of IEEE and the chairman of the Department of Mechatronics and Biomedical Engineering at Air University, Islamabad. His role as a tenured associate professor, along with his position as the head of Neurorobotics Research Group, reflects his commitments to advancing cutting-edge research and fostering innovation. Sir, your presence will undoubtedly enrich our discussions and inspire fellow members to aim for greater heights. Your vision, expertise, and accomplishments position works as a guiding light for aspiring engineers and researchers. Your presence in Bazm-e-BME Society marks the beginning of a collective journey towards advancing the frontiers of mechatronics and biomedical engineering. With open arms, we welcome you to our community.
So I hope that my voice is clear. Thank you very much for your introduction. And today is a great day. Honestly, let's forget about all the formalities. Uh, you know, being here with Professor Jonathan Wolpaw, it's a great day. I'm really pleased. I know when I started my journey in the field of brain-computer interfacing, um, the first few papers that I read were those by Professor Jonathan Wolpaw, along with I remember DJ McFarland and Niels Birbaumer. These were the authors, I always looked upon, and these were my inspirations, these people. Uh, I have not been able to meet Professor Wolpaw so far, but this is the first time that we meet in an online setting. and I'm really excited about it. Now, Professor Wolpaw does not require any introduction at all, honestly. Uh, I mean, one of the founders of EEG-based BCIs. He has more than 40 years of experience in this field. He's the director of a national Center for Adaptive Neurotechnologies at Albany Stratton Medical Center. So, I mean, uh, one of the pioneers of BCIs, the field that I work in, and EEG-based BCIs in specific. You can, see the number of citations that his papers have got, because, that was fundamental and primary work in the field of BCI. So, I mean, it's a great day. We all should be very proud of, this day. And thanks to Bazm-e-BME, actually. I mean, the platform that Saim and other people have created, I mean, it's remarkable. I mean, a few months ago, we could not have thought of anything like this, but this thing is happening now. So, I mean, I'm very excited about it. I won't, want Professor Wolpaw to wait much more now. I would like to give stage to him. I would give him a chance to speak about his topic today, which is making better BCIs. Let's, welcome Professor Wolpaw and listen to him. And after he's finished, then we'll have a chance to ask him some more questions and interact with him as well. Professor, the stage is yours. Uh, Professor, is your mic unmuted? Because I cannot hear you.
Somehow I had unmuted, hadn't I? I'm sorry, let me go back.
Okay, now it's fine. Yeah, I thought it was a problem at my end. Sorry.
No, it wasn't, unfortunately. Yes, anyway, again, I want to thank you for the opportunity to be here. It's very exciting to hear about the new society that you formed, how well it's doing, the excitement. There's a huge amount of work to be done in the field. I'm very glad to be able to hopefully make some contribution toward your involvement and development in this field. I've talked some with Noman in the last few minutes. I'm very interested in hearing about the 𝐹𝑁IR's work that he's doing, the hybrid work also. So it's very exciting for me also to be able to be here. So I'm going to be talking about making better BCIs. And I'll start out with a statement that existing BCIs are unreliable. I've sort of summarized this in terms of the Grand Canyon problem. At this point, anybody who doesn't have a death wish would never think about using a BCI to control his or her body or control the movement of a wheelchair on the edge of the Grand Canyon. They're just not that reliable. So the question is, why are they unreliable? We're still fairly early in the development, but it's been going on for maybe 40 years now, and this remains an issue. How can we make them reliable? And answering this question really begins with a more basic question, which is, what are BCIs trying to do? What's the goal? What do we think of BCIs as doing? So one interpretation that's very popular, and it certainly is very popular in the media and among the public, is that we're decoding the central nervous system. We're listening in, we're wiretapping, we're reading the mind. This is very nice. If it's fine if you're a reporter or you're the public looking at this. But it has some limitations. It means that basically it's given the focus on two kinds of approaches. One is bioengineering. We're looking for better ways to record nervous systems from the central nervous system. And the second is signal analysis, better ways to analyze these signals to figure out what people want to do, basically to read the mind, to decode the CNS. Now, I worked for many years, as Noman mentioned briefly, with Dennis McFarland, who unfortunately died now 4 years ago. We were very close colleagues going back into the mid-'80s. And we worked, he was at least as responsible as I for the development of our BCI program. We thought very differently, had different ways of going about looking at problems, but and big issues, we agreed. It took us a long time to figure out how to work with each other, but we finally understood that we were very different, but we did arrive at pretty much the same conclusions about big issues. And we analyzed what BCIs do in these terms, that the central nervous system, the brain and the spinal cord, acquires and produces adaptive behaviors or skills. That's what it's for. It gives us the behaviors, the skills that get us through our lives. From very simple things like the reflex that moves us quickly away from a hot stove to the most complicated athletic and cognitive skills. All the natural skills, all the things that we normally learn and do during our lives are produced by muscles. BCIs are a new thing because they convert brain activity, CNS activity, into non-muscular skills that replace, restore, enhance, supplement, improve, or emulate natural skills. So this is the basic figure that was in our BCI book now from 12 years ago. We're working on the second edition. And this is replace, restore, enhance, supplement, or improve natural skills, muscle-based skills. There's also an additional category here that we'll be in, which is emulate, which recognizes the fact that scientists are now using BCIs as a way of understanding nervous system function. So, but as a scientific tool, really. But this is the basic idea, that BCIs do these 6 things. So basically, BCI use is a new kind of skill. It's a non-muscular skill. Like natural muscle-based skills, BCI-based skills are learned. They're acquired through practice. And this is shown here, the work of Don Taylor and Andy Schwartz's lab now more than 20 years ago, as a monkey learns to use unit activity, single neuron activity recorded from the brain to control movement to a target in 3 dimensions. And as the animal gets better, the target radius can go down, performance gets better. This develops over days of practice. It's a skill that's learned. Similarly, this is from Jose Millán's lab, looking at how 2 people who were quadriplegic due to, I believe, to spinal cord injuries, learned how to use a BCI to control a very simple computer game. And this is EEG. It shows the focus of activity that they were using to control this game, one person and another person, over months of practice. And the activity gradually got better. They gradually learn to be better on this task. This is a skill that it was acquired. So when we say, what are BCIs trying to do? Decoding the brain is fine if you're a reporter or you're the public and you're excited about the possibility of reading the mind. But really what they do is to create new non-muscular skills, skills that are produced by brain signals rather than by muscles. And if this is what they do, then neuroscience becomes very important. We need the neuroscience that so that we can enable BCI skills to function like natural skills. That is, to be reliable, to be as reliable as our muscles are. So this is really the bio part of biomedical engineering. This is a very important focus. It's got to be more than just engineering and signal analysis. It's got to very much involve neuroscience. So in sum, because BCI use is a new kind of skill, BCI research and development can benefit from new understanding of how natural muscle-based skills are acquired and maintained. And that's really grown in the last 20 or 30 years. We know a lot more about how regular skills are acquired. A lot of things we thought 40 or 50 years ago were clearly wrong. So, and a part of this, a good deal of this, comes from this man, Nikolai Bernstein, who was a very interesting person in the early and middle 20th century. He worked in the Soviet Union. His work was really not known outside of the Soviet Union till really later in the 20th century. But he did very important work in movement control, in motor function, in a very, as I'm sure you probably realize, a very difficult environment. He had basically two problems which made his life particularly difficult. First, he was a Jew, which means there were certain positions that weren't open to him in the Soviet Union. He was under other sorts of restrictions. That was the first problem. The second problem was that he disagreed with Pavlov, who was viewed as sort of a god in the Soviet Union at that time. He didn't always agree with Pavlov. However, he was able to function very well. He made major discoveries, which, as I said, we're only beginning to fully comprehend in the West and know about. His first translations into English were made in a short book in the 1960s. And more recently, Mark Latache has translated all his major works. But here's one of the main things he determined. So this is a man about a skill. This is one of the things he learned about muscle-based skills. This is an expert who's using a hammer to hit the chisel at two different points. And this shows the trajectory of the hammer as he goes up and down each time. Now, what you need to see here is that the trajectory differs from one performance. This is an expert. This is someone who's really good at this. The trajectory differs from one performance to the next, but this doesn't differ. The hammer hits the chisel exactly right every time. Target 1 or target 2. That's very stable, but this is different. So that means that the central nervous system activity is not the same every time, even though he's doing exactly the same thing. You have all the various parts, as we know, of the central nervous system, cortex, thalamus, basal ganglia, etc. They all collaborate. They all interact to control motor neurons, which control muscles. And they get feedback from vision and from sensory receptors. So these are the areas that are producing the signals. The signals are not the same every time. The trajectory, as you saw, is not the same every time. The underlying signals from all these areas are not the same every time. So bioengineering and signal analysis alone will not solve this problem. It's not just detecting difficult signals. The signals themselves are changing. So that's a very important understanding, that the skill has an essential attribute which is kept the same, which is this, where the chisel hits. But all this stuff up here, the signals producing that are going to change from one time to the next. There isn't any fixed signal to find. So that's one thing that we've learned over the past 40 or 50 years. The second is that the central nervous system is changing continually through life. It used to be believed that the central nervous system was largely hardware, and the skills that we learned were stored away in special synapses somewhere in the cortex of the hippocampus or elsewhere that we had to find. And whenever we did the skill, that software that was stored away was just downloaded into the hardware. And that was a very neat idea. That was very, it was very appealing, and people looked for those modifiable synapses. However, it turns out that the reality is a lot more complicated and a lot more interesting. It turns out that the central nervous system is not mainly hardware. There's very little hardware. The entire nervous system is changing in many ways throughout our lives. The neurogenesis, new neurons appear, genes are activated, neuronal properties change, there's synaptic properties that change, long-term potentiation and depression, glia change, dendrites change, hormones change, there's sprouting of axons, there are even vascular changes. Somehow, all these changes, which are going on in all of us throughout our lives, somehow get coordinated so that we acquire and maintain all the skills that we do during our lives. So the other thing that has become clear is that the CNS substrate of the skill is a distributed network. It's not stored away in some special place. It's a distributed network of changes. For example, this is from a study in Doyen's lab in Canada some years ago, looking at the plasticity, the changes in the nervous system that underlie the acquisition of a simple finger flexion sequence task in people. So these are functional MRI changes that correlate with the acquisition of this skill. So there are changes in cortex, there are changes in basal ganglia, there are changes in cerebellum, and there are also changes in spinal cord. Changes in all these areas combine to produce overlapping and independent contributions to the acquisition of this skill. So this is a distributed network of neurons and synapses that changes so that this skill is acquired. We've spent a lot of time in my lab over the past 30 or 40 years looking at the basis of another even simpler skill. This is the operant conditioning of a very simple spinal reflex. And these are people in the lab who are responsible for this: Shenyan Chen, Yu Wang, Jonathan Karp, Lu Chen, and Yi Chen. And I'll just give you the summary of this. Is close to about 40 years work. This is how we understand this very simple skill, which is a lot. In this case, we're making this reflex smaller. That's what the skill is, to make a smaller reflex. And we understand, this is our understanding of how this occurs. The reward produces activity in the inferior olive, which produces plasticity, change in the cerebellum, which produces plasticity or change in the sensory motor cortex, which changes the descending activity in the cortical spinal tract, and that produces a small but significant decrease in the reflex. We're rewarding a smaller reflex. As that remains in effect over days and weeks, it produces plasticity change at many sites in the spinal cord. And as a result, you have a much bigger decrease in the reflex. So it appears that change or plasticity in the brain guides and maintains the plasticity in the spinal cord. So we have new knowledge. What I've covered in the last few minutes is new knowledge that we've gained in the past decades. A skill is not performed exactly the same every time. The central nervous system is plastic through life. The substrate of a skill is a network of neurons and synapses that goes all the way from the cortex to the spinal cord. These networks, the networks for each skill, the networks overlap. They share neurons and synapses. So that raises a new question. How do they maintain their skills in the continually changing CNS? When you acquire a new skill and it affects the same neurons and synapses that were responsible for an old skill, how is the old skill maintained? This requires really a new paradigm, which is for understanding the production of adaptive behaviors by the central nervous system. And that the heart of this paradigm is that these networks have two special properties. They have an individual property. The network changes continually to maintain the key attributes of its skill. For example, for the man swinging the hammer to hit a chisel, the key attribute is where of the trajectory is where the chisel hits. The trajectory in between can be different. The key attribute is that it hits the head of the chisel. For locomotion, for walking, there are multiple key attributes: symmetry, posture, balance, metabolic cost, not being excessive. These are the key attributes of locomotion. The muscle activity and the kinematics may change, but the key attributes are maintained. So this network is really like a person with one purpose in life, maintaining its skill. So that's the individual property. The collective property is the networks are all changing continually. They're changing the neurons and synapses that they all use. Each one is trying to maintain its skill. Thus, the aggregate process is essentially a negotiation. They negotiate the properties of neurons and synapses they all use. They keep the central nervous system in a negotiated equilibrium that maintains their skills. This is similar to a Nash equilibrium for those familiar with game theory. It's a situation in which each of the players reaches the best solution that that person can get with, because if he or she makes any change, somebody else will make a change and they won't be better off. So it's the best situation that each can reach, given the overall set of them. So the central nervous system substrate of a skill is a distributed network of neurons and synapses that produces a skill and changes continually to maintain it. This was presaged by Nikolai Bernstein when he said behaviors are biodynamic structures that live and develop. Together, these networks maintain a negotiated equilibrium in the central nervous system. And it became clear a number of years ago that they need a name that implies their special properties. So I followed really the same plan in doing this that Sherrington had followed in the 1890s when he needed a name for the connection between neurons. He went through various words like conjunction, injunction, etc., which were unsatisfactory. He wanted a name that would imply what he thought were going to be the key properties of this. And that's how they came up with the name synapse. He went to a Greek scholar and got an appropriate Greek word for this. That's where synapse came from. Anyway, so I did the same thing, consulted Adam Commissar, who was a classical scholar. We went through a long, very interesting process over the course of the pandemic. So I've never actually met him in person, but we had a very long correspondence and interaction. He found really a perfect classical word and we came up with the term hexors from the ancient Greek word hexus. This is a term that was originally defined by Aristotle and then changed some by the Stoic philosophers that followed him. But it really is a perfect term for what we're looking for, the CNS substrate of a behavior. And the fact that it has an OR ending means that it's an actor. It's an active agent. It is maintaining its performance. It's maintaining its skill. So these are hexers. This is the finger flexion sequence learning hexer, the distributed network, neurons and synapses that underlies that skill. This is our spinal reflex conditioning hexer, the distributed network that underlies changing this simple reflex. So this is a simple example of how this happens. This is one hexer. This is the nervous system Early in life, it has a whole bunch of neurons and synapses that can change, all these different, as indicated by the deltas, all these different properties. Early in life, we acquire, and this is in utero and early in life, flexion withdrawal reflexes. This is learned. They're learned, as Schoenberg's lab has shown over the course of interactions in the uterus and early in life. We acquire the rapid reflexes, flexion withdrawal reflexes that do this. And this involves changes in a network of neurons and synapses for flexion withdrawal reflexes. A little later, we learn how to walk. This changes an overlapping set of neurons and synapses to produce walking. And these guys here have to change because these guys changed, and these four still need to produce flexion withdrawal reflexes. So this is the negotiated solution. And even later in life, someone might acquire a sport, say throwing the discus, which leads to an additional negotiation. And I will just point out here that when you think about this negotiation, it's really very difficult and it has to be very complex because flexion withdrawal and walking are symmetrical. They're the same on the both sides of the body pretty much. So the changes can be pretty much the same on both sides of the body. However, this discus throwing is very asymmetrical. It's going to require different changes at all levels from the cortex to the spinal cord. At the same time, flexion withdrawal and walking have to be maintained. So the prediction here, and this we're now in the process of trying to test this, the prediction here is that flexion withdrawal, walking will still be performed just fine, but they'll be performed differently on the two sides. The key features of walking will still be there, posture, balance, symmetry, etc., but they'll be achieved somewhat differently on the right and left sides. So this is the central nervous system in a state of negotiated equilibrium. And here I want to finish up this talking about muscle-based skills with just a very simple example from our work. This is the work of Yi Chen. This is a rat walking on a treadmill. And you can see the right and left soleus muscle activity that's allowing him to do that. The burst for right stance and then for left stance. When we down condition, we make the H reflex of the soleus muscle smaller, that burst gets smaller. And when we make it bigger, that burst gets bigger because that pathway participates in the soleus burst. But walking is not impaired. The animal isn't tilted as it walks along. Walking is not asymmetrical. And that happens because the locomotion hexer adjusts. Here you see a rat walking along, its head is here, its hip, knee, and ankle angle. This is what happens when the reflex gets smaller. If all that happened was that the soleus burst got smaller, the hip would get lower. But that isn't all that happens. There's a compensatory increase in the hip angle. So as a result, the hip height stays the same and the animal is not tilted as it walks along. Similarly, when the reflex gets bigger, if this were all that happened, the hip would go up, the animal would be tilted the other way. But that isn't all that happens. There's a compensatory decrease here so that hip height stays level. The old locomotion hexer adapts to the new H reflex hexer. This is a little tiny piece of a negotiation. So a hexer is a network of neurons and synapses that produces a muscle-based skill and changes as needed to maintain the key attributes of the skill. Now, back to BCIs. A BCI creates a synthetic hexer. A synthetic hexer is a network of neurons, synapses, and adaptive software that produces a BCI-based skill and changes as needed to maintain the key attributes of the skill. So these are natural hexers. You saw these before. If we add a synthetic hexer, basically say one that is going to control movement, use a BCI to control movement on the edge of the Grand Canyon, you have these guys are involved, and you also have the adaptive software of the BCI. So this is a new player in the negotiation, and a very unusual kind of new player in the negotiation. I'm really getting here to why I think BCIs are unreliable. So, and to summarize this more, these are muscle-based skills. You saw this before. All these cortical, all these brain areas collaborate to control muscles. Here are the multiple hexers that have a negotiated equilibrium. They all agree on, they've all achieved a solution that allows all of them to produce their skills appropriately. And this is a BCI-based skill. You have all these cortical areas. Say you're taking activity from the cortex, say single neuron activity, sensory motor rhythms. You're sending them to a BCI, which is then producing the skill. So here you have a synthetic hexer, which involves the BCI and the central nervous system. Everything is now being adjusted to produce appropriate output here to go to the BCI to produce the skill. So when you think about adding,
Oh, Professor, you're muted again now. Oh,
okay. Yeah, I don't know
no,
how
it's
that,
fine.
yeah,
It's okay.
how long was I muted?
Just now you got muted, and I told you. Yeah.
All right. So anyway, this is this is the situation when you combine muscle-based skills and the BCI-based skills. And as I said, the first time I made this slide, I said, boy, I can't show this. It's just a mess. But that's the point. It is a mess. And this, I think, is the basic reason at the present time why BCIs are unreliable. You have this unusual kind of new skill that is trying to share the same neurons and synapses with all the normal muscle-based skills. So basically, it winds up being the loser in whatever negotiation manages to occur. So going back to the question, why are BCIs unreliable? The negotiated equilibrium is dominated by natural hexers. Synthetic hexers lack advantages that natural hexers have. Relevant basic science questions are not yet answered. Things like how do hexers negotiate? How do they retain their key attributes? How do they change in the absence of performance? For example, we know that you can learn to ride a bike when you're a kid, and 50 years later, you can still ride the bike reasonably well, even though you haven't done it in between for 50 years. Your body has changed. A lot of things have changed, and you can still manage to ride a bike reasonably well right off. That means that somehow that skill has been maintained, even though it hasn't been practiced. Somehow it's using the result, the feedback from other skills, from other hexers, but that's clear that they do change productively, successfully in the absence of performance. Now, given all these problems, nevertheless, synthetic hexers could be given, even in the present time, some of the advantages that natural hexers have. And I think if we can do that, we can go a long way toward making BCIs more reliable. First, the synthetic hexer needs an appropriate starting point. We're already basically doing this in teaching the monkey how to use cortical neurons to control movement of a cursor. That started with the activity of those same neurons in actual muscle-based control. So it started with a similar situation. And similarly here, you have a starting point of sensory motor rhythm desynchronization, and you gradually learn how to focus that on the control that you want. So an appropriate starting point is essential. Second, and this is now being pursued more, a synthetic hexer needs better sensory feedback. Most BCIs at this point use visual feedback, which is slow and doesn't have a lot of specific information in it. This is from a review showing that people are now beginning to use electrical stimulation of sensory motor cortex to provide feedback, say from a robotic arm, which the new synthetic hexer can then acquire the ability to use to produce better and more reliable movement. So this is one potential way of improving BCIs, and this is now being pursued by a variety of labs. A synthetic hexer needs signals from multiple areas. As you saw, multiple areas interact to produce muscle-based control. Normally, up to the present, BCIs have used activity from one cortical area. This shows the advantage of multiple areas. This is from a review by Gallego et al. Recently. This is, for example, many studies have used primary motor cortex, and the idea is to find this motor command in primary motor cortex. However, that's there, but there's also other stuff there. There's activity. There's activity that's associated with attention. There's activity that's associated with unexpected somatosensory feedback. And if you look at other cortical areas, such as prefrontal cortex, you can see attention. You can get activity associated with attention, and you could then take it out of here, in theory. You could get it out of here to get back. So instead of having this messy signal here, you manage to get back closer to the isolated motor command. Similarly, unexpected sensory input can produce, you can see that here when you go to primary somatosensory cortex. You could take that out with, if you were also recording from here, and get back toward the isolated motor command. So this is another way of making BCIs more reliable by eliminating from this cortical activity, from the motor cortical activity, the parts that aren't really associated with the motor command. A synthetic hexer needs redundancy. As you saw, there are multiple ways for muscle-based hexers to achieve their key features. A natural hexer can use different combinations of muscles. This flexibility facilitates skill maintenance and negotiation. So for example, after you learn how to play the discus, how to throw the discus, your walking may use somewhat different combinations of muscles on the two sides. So, and you saw here how there were going to be differences that allow walking to continue to maintain its key features, such as stable symmetrical hip height, despite the impact of the new hexer that we've created. Synthetic hexers typically lack this critical advantage. They basically use just fixed locations and fixed analysis of activity from those locations. A synthetic hexer needs redundancy so that you could get the same skill from different selections of the available neurons, synapses, EEG rhythms at various locations. A synthetic hexer also needs key attributes that it maintains. A muscle skill changes continually. It has key attributes that are maintained, such as here. This is what's being maintained in the trajectory. This is varying. So BCI skills need key attributes. For example, here would be things like posture, balance, symmetry, and the other aspects that would be essential for controlling your body or the movement of a wheelchair on the edge of the Grand Canyon. And the last thing that I'll mention here is the most difficult, because we understand the least about it, that a synthetic hexer needs to negotiate with natural hexers. You really want to help synthetic and natural hexers play well together so that they can reach a negotiated equilibrium. This could be this could be done with a special, perhaps with a special kind of hybrid BCI. Could be parallel performance, in which you are controlling two dimensions using a BCI signal for one dimension and muscle for the other. Really, urging, compelling these two outputs to function together, to cooperate. Or it could be sequential performance, in which you went from one location to the next using the BCI, and then for the next period you use the muscle, then the BCI, then the muscle, then the BCI, etc., to really force them to interact. Finally, a synthetic hexer needs ongoing updating. Natural hexers appear to undergo continual updating. Spontaneous activity may reflect interactions among hexers. Natural hexers may be guided by changes in related hexers and related skills. Previous steps may enable synthetic hexers to be similarly guided, for example, by giving them joint exercises, either in parallel or in sequence. Otherwise, real understanding of how to do this really must await better understanding of ongoing hexer interactions. And there are some obvious studies that are beginning to be undertaken that will give some insight into that. So finally, in summary, BCIs create non-muscular skills. Therefore, in developing BCIs, we can be guided by muscle-based skills. The skill substrate of a muscle-based skill is a network of neurons and synapses that we're calling a hexer. Hexers change continually to maintain the key attributes of their skills. They keep the central nervous system, neurons and synapses in a negotiated equilibrium. BCIs create synthetic hexers, a hexer that's a combination of central nervous system neurons and synapses with the BCI software. Now, at present, BCIs, synthetic hexers, are pretty unreliable. How do we integrate them into an expanded negotiated equilibrium? They need appropriate starting point. They need sensory feedback. They need signal from multiple areas. They need redundancy in terms of being able to use different combinations of signals, of locations, to produce a given output that has the essential key attributes. The ability to negotiate, ongoing updating. While bioengineering and signal analysis are certainly important, creating better BCIs is really probably first and foremost a neuroscience problem. So there have been a lot of people involved at NCAN and with our collaborators in this. Again, I want to particularly emphasize my long-term colleague and friend, Dennis McFarland, his huge contributions in the field, which I imagine you're aware of. We have support from NIH, from the Department of Veterans Affairs, and from other organizations. So thank you very much. I look forward to your questions and comments, and I expect that I'll learn as much as you will from my answers to them, because often people bring up things that I just hadn't thought of before, because this is all pretty new. Thank you very much.
Well, thanks to you, Professor. I mean, it was amazing. I mean, I've been working in this field for a long time now, but the concept of hexers was new for me even. I was not able to read this paper of yours. So this is a very interesting idea and, has given me a lot to think upon. So thank you very much for your interesting talk.
I'm very interested in your, I can put in the chat, this is the basic reference that came out now 2 years ago. And it's got a lot of background that obviously I couldn't put into the talk.
Okay. So now I would request the audience to ask questions if they have any. And I mean, if you want to ask in a voice, then you can just raise your hand and I'll allow you to ask questions. Or if you want to put it in a chat box, you can do that too. So if you have any questions, I'll, okay, so we have one question from Haroon Ahmed. So Haroon, you may please ask your question.
Hello, this is Muhammed Sajid, actually, from University Multan campus.
Okay.
I'm a student of PhD in computer science, and I just need to know how we can relate BCIs to computer science for future research, how we can do research related to computer science and with biomedical, this BCIs concept. Thank you.
Okay. Yes, thank you. That's a very good question. I mean, clearly computer science is very much essential for this and very much involved in it. I mean, my background is primarily biomedical. So, I mean, my effort, my emphasis here is that it is important for everybody in this area to at least acquire some neuroscience background, to be able to know, be able to follow what I was talking about in the terms and think about it from those points of view. And that's something that the whole BCI field is extremely interdisciplinary. And that's something that took a long time to work with. I mean, it was really interesting when the field first began in the 80s. You had the engineers who thought they were the only ones in the field, and you had the psychologists who thought they were the only ones in the field, and you had the neuroscientists who thought they were the only ones in the field, and they barely even knew about each other's existence. That's changed a lot. The BCI Society has had a lot to do with that. The joint meetings over the years has had a lot to do with that. And that's essential because this is a very interdisciplinary field. And I really urge anyone who, in whatever your basic, whether it's computer science or whatever, if you want to be in this field, you need to learn also to some extent what's going on in the other disciplines. Because to produce these things, it takes all the disciplines working together. And you don't have to be an expert in all of them, but you need to be able to interact with people in other areas and understand what their problems are, and then what their perspective is. And computer science is obviously very fundamental to this whole thing. I mean, that's how BCIs operate. And so that, I mean, it's really important, but you need to gain the broad perspective and to have some multidisciplinary insight. I mean, I'm clearly not an expert in just almost all the areas that are involved here, but I have some familiarity and can engage with people in each of them, and other people are doing that as well. That's really essential. That's why at our center we've stressed having courses. We had a 3-week course that we taught. It was supported by NIH for a number of years that basically went through the whole field, from the basic science all the way to the ethics at the end, with computer science and everything else in there, to give people an overall perspective. But those kinds of things are really, we have the curriculum for that available. We do teach various aspects of it in virtual or combined virtual and real life courses. But that's the main message I have for you.
Okay, great. So we have a question from Fiza Farouk. Fiza Farouk, you may please ask your question, and first, please introduce yourself.
Hello, I'm Fiza Farouk, and I am actually an assistant professor at the Department of English. Basically, I have a PhD in linguistics, and really interested in knowing more about BCIs. And today's lecture was amazing. I first have to say that. So my question from Professor is, you've worked in this field for such a long time. You've talked about the theory, the application, and all of the involvement in terms of biomedical engineering and sensing, processing. I want to ask you is, where do you see this BCI system going from, like, as you mentioned, being unreliable at this point, but after like 10 years or 20 years, where do you see this BCI technology, this BCI idea going ahead in the future? Where do you see it? I mean, how do you see it?
That's a really good question. That's a really good question. The thing that certainly the public likes, and it's really been very interesting for me because I've been seeing this now, watching kind of for 40 years, that the press and the public, and it seems like they discover BCI every 6 months, and they forgot that they discovered it 6 months ago. But and the focus is on the mind reading part of it, and those things that are kind of very high profile and appealing. But I think the real importance of this in the short term and the medium term is really going to be for rehabilitation, because it's clear that you can use BCIs to improve rehabilitation for after a stroke, after a spinal cord injury, because there in those situations, I mean, getting back, you're trying to take, you know, damaged hexers, damaged locomotion hexers, damaged speech hexers, and you're trying to restore them. There are ways that you can use BCI-based signals to guide that restoration, to enable them to regain their key attributes, to function better. So the use in rehab is just beginning, but I really think it's very important. The other reason is it doesn't have to be perfect. You know, it doesn't have to help absolutely everyone. It doesn't have to work every time. It doesn't have to be totally reliable. It has to add value, and there's evidence that it does add value. So that's a very potentially valuable use of BCIs. At the same time, the BCIs are being used, as I mentioned, by Aaron Batista at Pittsburgh and others to examine how the nervous system functions. You know, people do this with neural networks. They do modeling of central nervous system function. Well, you get a little closer when you can actually use the cells, the neurons themselves, and set up interactions. You can set up skills based on the neuronal activity, see how they develop. In fact, some of the evidence that we now have for negotiation comes from those studies. The interactions as people, as in this case monkeys, learn to use combinations of neurons to do one thing and then learn to do another. And basically what you wind up with is that the two skills, you get a negotiated solution, so that they come up with activity that really serves, that is a combination of what each skill requires. So that's another potential use, the scientific uses of this. In terms of the actual decoding, that presumably will come, but it's going to be a while. To do that on the edge of the Grand Canyon, it's going to be a long time. The other uses, less critical things like communication, where you can make a mistake, etc., those will come probably somewhat more, are coming more rapidly. But it really has to be that people really have to get away. I mean, the scientists doing this, the engineers and the scientists doing this have to get away from the idea that they're decoding the brain. What they're doing is working with the brain. They're trying to enable the acquisition and the maintenance of a new kind of skill. And taking that perspective makes a big difference in how you go about it and what you can achieve. So.
Okay, so do we have other questions? Anyone else? So we have Rabab Khan. Kindly ask your question.
I am Rabab Khan from UET New Campus, currently pursuing biomedical engineering as an undergraduate.
Yes,
so my question is, in your opinion, what do you think will be the breakthrough technology, or you can say innovation, that could make BCIs mainstream in the next decade, and why?
Well, I think they could be mainstream for rehabilitation in the next decade. Things have to be pursued. There's nothing, for that to happen, well, there's another aspect, okay, which you bring out in this too, which you have to come up with solutions with applications that are not just, really exciting scientifically or even interesting clinically, but they have to be practical for actual use, for incorporation into ongoing clinical practice. I mean, I'm focusing on, say, rehab applications, rehabilitation. How do we make function better after a stroke, after a spinal cord injury? Those are the immediate, really potentially very impactful uses of BCIs. So what you need are and this can, you need studies that show that this works and this is good. And you need controlled trials. You need to compare it to what happens without. Donatella Matea in Rome has done some of that now for stroke rehab with sensory motor rhythms. There needs to be more of that. There can, a lot of this, particularly with, it also emphasizes EEG, because if you can do this non-invasively, that's very nice. So for rehab, those kinds of, that's where it will happen, I think, that where it can happen, but it has to be, this is another reason why the multidisciplinary background is necessary. You have to at least understand all the problems that go from the basic science through the initial lab work, through the animal or human work, to the initial human applications, to the actual human improvements and controlled studies. And then you have to figure out, okay, how's this going to be put in a device, on a procedure, which can actually be provided to clinicians to use, that will be able to be commercializable so that it can be widely distributed, that the various parties involved will be willing to support. There have been applications, very potentially useful applications, which just haven't gone anywhere because there isn't the correct incentive structure, so that the clinicians, there's no, it can't be put in a position where this is something they can practically do in terms of reimbursement, in terms of time, et cetera. All these problems have to be solved to really get this stuff out there. I mean, have basically been pretty much a basic scientist all my life, and it's only been the past 10 or 20 years that I really sort of become aware of these things that have to happen if what we're doing in the lab is really going to wind up helping people. And those are interesting problems also. So as a result, we're now working with companies to try to get through this, but it's difficult. And in terms of the overall understanding of how you make BCIs really reliable, there's a lot of basic science that has to be done. A lot of it. The problems are now clearer, I think. In our paper, and 2 years ago, talks is related to that, to some of that. We have hopefully a large paper about neuro rehab coming out, hopefully in the course of the next year, that'll get more into that. But there's just a lot of basic science that is necessary for the, for BCIs to become completely reliable for all sorts of tasks. Go ahead. Sorry. Yes.
Oh, so someone else was asking some question, I believe. So who was that? Okay, Muhammad, you can go ahead with your question.
Hello, sir. So my name is 𝐌𝐢𝐧𝐝 biomedical engineering sophomore from University of Engineering and Technology, Lahore. So my question is, how can BCI researchers and developers ensure that user experience is prioritized alongside the technical performance, particularly in the clinical?
Second part, how can they ensure what? What can you, the second part of your question, how can they ensure?
The user experience, he said, along with the technical expertise, the user's experience.
How can they ensure that?
Yep, that's what he was asking.
The user experience is prioritized alongside the technical performance, particularly in clinical and consumer applications, sir. And sir, there is a second part to this question, that what are the impact of the environmental conditions on the synthetic exerts, sir?
Oh, okay. Well, that's very important. I mean, obviously, yeah. I mean, that's one of the major questions, and we need, I mean, the basic sciences will be important in that, because clearly, you know, we can walk satisfactorily in all kinds of situations, you know, in both internal situations and external situations. We can adjust. That will be something that will have to be part of that is, I mean, the getting signals from multiple areas will be very important in that, because then you will, the BCI will have input that indicates how things have changed elsewhere. You know, it's kind of like if you're in, you know, you're sitting in a boat and the water is very calm. If you raise your hand up and down, then the position of your hand is being controlled by you moving. But if there are waves and there's wind and the boat is moving all over the place, what you do with your hand is only part of what controlling the hand position. So, I mean, we really need to get that wider perspective. So you're bringing up the environment is really important. And some of that is going to really come from giving the synthetic hexers the same capabilities, because if we can give them the same capabilities as natural hexers, it will happen. They will acquire that reliance and that stability the same way natural hexers do that. But right now we're a long way from knowing how to do that, but that will be a very important part of what happens.
Okay, so Sayed, you raised your hand. Sorry, I couldn't get your question first, but you can ask now. Sayed Anas? Yes, please go ahead with your question. Yes, Sayed Anas, you can unmute yourself and ask your question. Oh, so any other questions, please? Okay, if not, then let's go towards the conclusion of this exciting and wonderful webinar. I generally do not like to listen to online talks, but yeah, this one was different, primarily because it's directly related to the area that I work on. And of course, it is given by someone who I admired all my life. So yeah, I mean, it was amazing experience. I would now like to, thank you, John. I mean, I cannot thank you enough. Thanks a lot for taking out time for us.
To meet you, and I hope to see you at BCI meetings or other places. It's really exciting to hear what's going on, and all the excitement you guys have. That's really neat. So definitely, I hope I've helped that. Yeah, I mean, this is really, it's great to see this. It really is exciting.
Truly. So now I would like to ask Syed Saim, who's representative of this newly formed community, Bazm-e-BME. He's one of the co-founders of this community as well, for a few words, and he will give the concluding remarks and conclude this seminar. Yep. Please, Saim.
Thank you.
Thank you, sir, and respected Dr. Wolpaw and Dr. Numan Nasir. Sir, we all are very grateful to you for sharing your qualitative research work with us. We are greatly inspired from your kindness and the love for the knowledge. The students of biomedical engineering truly learn a lot from you. We are thankful to the students and faculty members from Pakistan, from India, from UK and other countries for attending this webinar. And we assure you that we will continue collaborative work with the same zest and same patience and same perseverance. May Almighty Allah bless you with the best. Thank you, sir.
Thank you.
All right. I hope to see you soon somewhere.
Yes, me too. Me too. Thank you again. It's great.
Okay, thank you. Okay, take care. Take good care. Have a good day.
You too. Bye-bye.
Bye-bye. Yeah.